welcome back. So today we will solve the 2D elasticity problem using quadrilateral element. So first we will use the rectangular element, and then we will use the isoparametric element, isoparametric quadrilateral element. So let's draw the rectangular element first. So this we have done already for the 2D heat transfer problem. So we will use the exactly same setup. So this becomes 0 0, which is element node 1. Node 2 will be L 0, node 3 will be LH, and node 4 will be 0H. Okay, so this is X and this way is Y direction, and all nodes have 2 degrees of freedom. So there will be ux1 here and uy1 here, and similarly for all nodes. So ux2, uy2, ux3, uy3, and here also will be ux4 and this direction uy4. Okay, if this is the element, the idea is to find out the stiffness matrix we have to construct. So in this case we have to find out the expression. First, the expression we know already, so we don't have to actually derive it again. We have derived already for any number of nodes. So Ke, we know that this is given by then integral over the whole domain omega, and this will be T d b d omega. Okay, and if you recall from the last few lectures, B is nothing but, in this case there are 8 of them. So accordingly this will be the 3 by 16 3 by 8, sorry, 3 by 8 matrix. Okay, so let's write this way. So where B is equal to del S over del S n, okay, and where not B but let's say n is equal to, in this case will be n1 0, n2 0, n3 0, n4 0, and there will be n0, n1 0, n2 0, n3 0, and n4. Okay, so this is as we derived earlier. Delta S, del S is given as del over del x 0 0, del over del y, del over del y, del over del x. So this is del S, and if we use B equal to del S n, we will be able to find out B So, B, if you remember, B is nothing but del n1 over del x 0, del n2 over del x 0, del n3 over del x 0, del n4 over del x 0. Similarly, this one is del n1 del y 0, del n1 over del n2 over del y 0, del n3 over del y 0, del n4 over del y, and here del n1 del y, del n1 del x, del n2 del y, del n2 del x, del n, similarly here let's write here. So, del n3 del y, del n3 del x, del n4 del y, del n4 del x. So, this is how this matrix will be. Okay. So, so far all those things equations we have derived already in the beginning itself, and all these are here n, a small n equal to 4, hence you have n1 to n4, and hence you have B B as a matrix whose size is, whose dimension is 3 by 8 in this case. Yeah. So, next thing is to find out what really n is in terms of x and y, and this is easy. If you look at the element and you can automatically construct it. How will it look like? It will look like n1 will be this line and this line. So, we multiply them and see what is the value at 1, and accordingly we will have a coefficient which will make n1 equal to 1. So, that really means n1. So, n1 will be equal to equation of that. Okay, so that will be x equal to L, and this is y equal to h. So, we will have x minus L times x minus h, so that when x equal to L, this n1 becomes 0. When x equal to h, n1 becomes 0. But this has to be 1 when x equal to 0 and y equal to 0, sorry, here it should be y. So, n1 has to be 1 when x equal to 0, y equal to 0. So, you put that value here, you get L times h. So, hence coefficient will be over LH. So, you get n1. Similarly, you get n2. So, n2. Now, n2 here you have two lines here, this and this. So, becomes x equal to 0 and y equal to h. The x equal to 0. So, we write x equal to 0. So, x minus 0 and y minus h will be there. You put value again, the at node 2 n2 has to be 1 and xy is L0. So, you put xy here, x equal to L, y equal to 0. So, we get minus LH, hence we get minus 1 over LH. Okay. Now, we can use n3 again. For n3 these two lines are there, the x equal to 0, y equal to 0. Yeah, so let's write n3 here. So n3 is equal to x equal to 0, y equal to 0, hence x and y. However, at value LH, n3 has to be 1. So if it is L, this is H, so divided by LH. So this makes it n3. We now find out n4. Okay, for n4 we have these two lines. So y equal to 0 and x equal to L. So x minus L and then y. Okay, now the value n4 has to be 1 when at node 4, and node 4 has value of y equal to h and x equal to 0. So you put 0 here and h here, you get minus LH. So we divide by minus LH here. Okay, so this is what we get. So basically this is a combination of x minus L, x minus L and x, and y minus h and y. So we have y in two of them, y minus h in two of them, and then x in two of them, and x minus L in two of them. Okay, and they are scaled such a way that n1, n2, n3, n4 are either 1 or 0 at those 4 nodes. Okay, again this is not the new thing we are doing here. We have already done this when we studied the 2D heat transfer problem. So we are just rewriting it here, but it is exactly the same thing. Once we have n1, n2, n3 and n4, finding the B matrix is very easy. We just have to differentiate with respect to x and y, and since n1, n2, n3, n4 are explicit function of x and y, we can very easily find out these partial derivatives, and we put in this B matrix. Once we get this B matrix, we have here, and we can find out the corresponding stiffness matrix for the element. So it's very easy. Okay, so let's now just differentiate this one, okay, and then see how it looks like. So let's write n1 first. So we have n1 xy is equal to 1 over LH and x minus L and y minus h. Okay, so now what we need is del n1 del x. So we can write it very easily, and you get 1 over LH y minus h, and similarly del n1 del y is equal to 1 over LH and then x minus L. Okay. Now n2 equal to minus 1 over LH, and then you have x y minus h. So that will give you del n2 over del x equal to minus 1 over LH y minus h, and del n2 del y is equal to minus 1 over LH x. Okay. Now n3 we have 1 over LH xy, and so we get del n3 del x equal to 1 over LH y, and del n3 over del y is equal to 1 over LH x. Now n4 equal to minus 1 over LH, and then x minus h x minus L, sorry, x minus L times y. Okay, so del n4 over del x is equal to minus 1 over LH y, and del n4 over del y is equal to minus L over h x minus L. Okay, so once we have that, it's very easy to reconstruct the B matrix. So B matrix B, as we know, is equal to del n1 del x0 del n2 del x0 del n3 del x0 del n4 del x0 and 0 del n1 del y0 del n2 del y0 del n3 del y0 del n4 over del y, and then we have del n1 del y del n2 del n1 del x del n2 del y del nx del n2 del x del n3 del y del n3 del x del n4 del y del n4 del x. Okay, so like this one. Okay, so once we have that, we can actually put the actual values from here, and we'll find out the B matrix. So B, let's write the B here, but we will write in terms of B transpose. Okay, so B transpose is equal to, so that we have a big space here. So B transpose will be equal to, first this is the same matrix as this one, but B transpose, so this, the column becomes the this row becomes the first column now, and this column becomes the row now. So we will have the first one del n1 del x. So del n1 del x is 1 over LH. So let's put 1 over LH outside. So the first one del n1 del x is equal to x minus L, so we write x minus L here. Then we have 0. Okay, then we have minus x, so write minus x here. Then again 0. Then sorry, we have y minus h, 0, then minus y minus h, and so on we have to write. Okay, so del n1 and del x is here, so it's not y minus x minus h, this will be y minus h, 0. Then again here minus y minus h, so minus y minus h, 0. Then the third one, so third one here y, just y here, so write y, then we have 0 here, and then so y, then minus y. So here it will be minus y here. Okay. Okay, so and here this will be 0, then here will be the n1 del y, so x minus l, so x minus l here, x minus l, then we will have 0 here, 0 here, then here we will have minus x, so minus x, then 0, then x, then 0, and here also there will be 0. Okay, so has to be 8, 1 2 3 4 5 6 7 8, 0, and the last one will be this one, minus xl, so minus x minus l. So we have x minus l minus x minus l minus x. Similarly we have similar trend here. So these are the two columns we get. Now next will be the we can construct from here, so this will go here, so this is x minus l, okay, then y minus h, so this is del n1 del y, so this is this, and then this is del n1 del over del x, so that's why it's here. Okay, and then you'll have minus x here. Okay, and then minus y minus h, x, then y, then minus x minus l, then minus y. So this is what we get as B transpose. It's all these things is a B transpose. So once we have that B transpose we have now, so then K E is equal to this BT dB d omega, and now B T is as a explicit function of x y, so it can be integrated very easily. So we can write it as y will vary from 0 to h, and x will vary from 0 to L, and then we have bt dB, and then we have dx dy. Yeah, and this can be easily integrated analytically as well as numerically. Okay, so B is known here, D is again D is a material property that for the plane stress problem you already know, this is equal to E over 1 minus nu square, and then 1 nu 0 nu 1 0 0 0 1 minus nu over 2. So this is just one example which is for plane stress problem. For plane strain problem this will be different. Okay, so we have D here and we have B transpose and hence B as well, and we can very easily integrate that. Okay. Once we have the B matrix, we can find out the stiffness matrix, and we can also find out the force vector. So, force F, we said F B vector. So, a B is a B vector is given by is equal to integral over the whole domain, and n t b d omega, and f t, this is because of the boundary tractions. So, this is goes like this, n t and t and d gamma, where of course b is equal to bx and by, two components in the both the direction. This is a body force components in both the directions, and similarly the traction will also have a component in x direction and a component in y direction. So, this way we find out the element force vectors. So, we add them together. So, element force vector, so this F E, that becomes F B plus F T, like this one. And let us say if we had only one problem is something like this one. So, only one element it has like this one, then the equation will be K E and U is equal to this will be U E is equal to F E, like this one. Okay. So, where U E transpose is equal to, or U E equal to will be U x 1, U y 1, U x 2, U y 2, U x 3, U y 3, U x 4, U y 4. Okay. So, the boundary condition accordingly can be applied, and as we have been doing always, and you can solve the problem. So, that really means that main thing here is the finding out the stiffness matrix. Once you have that, this you know already, this is how they are. If you can find out by these equations, and you apply the essential boundary condition on this one. If for example, in this case U 1, 2, 3, 4. So, this is U x 1, this tells you what? This tells you U x 1 equal to 0 if it is fixed, and U y 1 equal to 0, U x 4 equal to 0, U y 4 equal to 0. Okay. So, accordingly this can be put here, and this equation can be solved. Once you have found out U, then you can use this to find out other things such as a strain. So, as you know, a strain is the strain is equal to U n, this is del S then n and NUE. So, this is what the strain is. So, that is equal to BUE. Okay. So, B is in this case 3 by 8 and this is 8 by 1. So, this strain you get 3 by 1. So, there will be 3 component of the strain, but since B is a function of x y as we have seen here, this B is a function of x y, hence the value of the strain will also be a function of x y. That means strain will vary within the element. Okay. So, please solve the problems from the exercise in your textbook in order to understand more actually. So, we will also do the numerical, we solve the numerical problems later in tutorials, and since this takes a lot of time because of the number of degree of freedom. So, you can solve these problems using computer programming. Okay. If you want to find out the stress within the element, then you can use this this equation. You know sigma is related to the strain with this D matrix. So, D matrix you put and multiply it by a strain and you get the sigma. So, in terms of this will be simply equal to D B U E and you get the sigma like this one. Okay. Again, since B is a function of x y, you will find that sigma also varies within the element. Okay. Though it will vary linearly as B matrix linear in x and y. So, that is why this will be sigma will linearly vary within the element. Okay. Now, let us say the quadrilateral element is not as simple as the rectangular element that we have solved. If the element could be something like this, okay, and this is a x y system. So, this is x and y here. So, what we can use is the isoparametric element that we have done earlier. So, we will have to convert basically from this system, irregular quadrilateral system, to xi and eta system that we have done earlier, such that let us say 0.1, 2, 3, 4 becomes nodes 1, 2, 3, 4 here with coordinates equal to -1, -1, 1, -1, 1, 1 and here -1, 1. Okay. So, this transformation we have to do, and how can you do that? So, this transformation can be done with respect to xi and eta such that you have x which is a function of n I x I like this one. Okay. So, here x is here x1 y1 x2 y2, these are the coordinates of the x3 y3 and x4 y4. So, these are the coordinates, and this x can be given in terms of x 1 x2 x3 x4. Similarly, y will be given as ni yi from I 1 to 4. Similarly, here on y I equal will go from 1 to 4, where ni is a function of xi and eta and will be got from here. So, this is isoparametric element, but this we have done already. Okay, so isoparametric element. Okay, so this we have again done this when we studied 2D heat transfer problem. So, nothing new, we are just applying this to the 2D elasticity problem. The basic definition of the shape functions remains the same. So, ni this one will be given by, so you can write it as, so here you have to find out for this one. So, this or this one. So, this equation is xi equal to 1. Okay, so you can write xi equal to 1. So, xi minus 1 and this is eta equal to 1. So, eta minus 1. Okay. If you put minus 1, so this becomes total 4. So, divide by 4. So, this becomes n1. This becomes n1. Okay, so what about n2? So, n2 xi eta is equal to, again here this one, so this and this. So, this is xi equal to 0, this is eta equal to xi equal to minus 1 and here eta equal to 1. So, this becomes xi equal to minus 1. Okay, and eta equal to 1, and we put value of this 1 minus 1 here. So, 1 here, minus 1 here, and we get minus 4. So, minus 1 over 4, get n2. n3 xi eta will be equal to, here eta equal to minus 1 and xi equal to minus 1. So, we get xi equal to minus 1, eta equal to minus 1 both, and we know that if you have 1 1, then you should get 1. So, 1 1 becomes 4, so divided by 4. So, this is what the equation is. n4 xi eta will be equal to, again this point. So, this and this. So, xi equal to 1 and eta equal to minus 1. So, xi equal to 1 and eta equal to minus 1. Okay, and the minus 1 if you put here minus 1 and 1. So, becomes minus 4. So, becomes 1 over 4, minus 1 over 4. So, this is what our n1, n2, n3, n4 are, and x is defined like this one. Okay. Okay. Now, everything here, what I mean is n1, n2, n3, n4 are in terms of xi eta, and x is related to this xi eta. So, there is a correspondence between x and xi, or from this coordinate system to this coordinate system. So, I am going to repeat what we have seen in the video lecture now, maybe last to last or in last 2 video lectures. So same thing we extend here basically, and this we have done in other video lectures as well when we were studying the 2D heat transfer problem. So we can write dx is equal to del x over del xi d xi plus del x over del eta d eta. Okay, and similarly dy equal to del y over del xi d xi plus del y over del eta d eta, or you can write it as dx dy is equal to dx over d xi dx over d eta dy del y over del xi del y over del eta, and here you have d xi and d eta. We call this matrix as the Jacobian matrix. Okay, so this is Jacobian matrix. We can actually find out the Jacobian matrix from here. Okay, so if we differentiate x with respect to xi, finally this will be this one being differentiated with respect to xi, and this and this and this all. So this is how we can find out, right? So we also know d del n I over del xi will be equal to del n I over del x over del xi plus del n I del y over del xi. Similarly, del n I del eta is equal to del n I del eta del y del x actually del x del x over del xi plus del n I over del x del y over del, sorry, there's a lot of mistakes in this one, so let's write like this. So del n I del eta equal to del n I del x over del eta plus del n I over del y and del y over del eta. Okay, or we can write it as del n I over del xi del n I over del eta, okay, is equal to, there is a matrix here and a vector here which will be del x del n I over del x del n I over del y, like this one. So if you look at here, so this will be del x over del xi, and here this will be del y over del xi, here del x over del eta, del y over del eta. And if you compare it with the Jacobian matrix, this will turns out to be J transpose of that Jacobian matrix. So, this you can write it as or del Ni over del x del Ni over del y is equal to J inverse transpose, and we write del Ni del xi del Ni del eta, like this one. Okay. So, this what we get, the relationship between n being differentiated with respect to x, y, and that with respect to xi and eta. This is the what the relationship is. Okay. So, remember that our Ke is given by B transpose dB d omega. So, this is in xy, coordinate system. So, xi is basically in xy domain. We have to actually integrate this one, or we can also convert that into xi eta system by converting this system to that, and we have seen that in one of recent lecture videos, last one or last one. So, this j d omega will be nothing but j times actually this d omega, and where omega is with respect to xi eta system. Yeah. So, where B has to be converted into xi eta system, okay. And it can be converted how? Because we already know the relationship, and what is the relationship we have? We know that B matrix has, we have seen several times today also, that this will have del n1 over del x 0, del n1 over del n2 over del x 0, del n3 over del x 0, del n4 over del x 0, and here it will be 0, del n1 over del y 0, del n2 over del y 0, del n3 over del y 0, and del n4 over del y, and here del n1 over del x y, del n1 over del x, del n2 over del y, del n2 over del x, del n3 over del y, del n3 over del x, del n4 over del y, del n4 over del x. Okay. So, this is what the B is. So, we have to find out the values of del n1 over del x, and how to find out? We have to find out using these relations. So, in order to find out this one, we have to know this, and this can be found out very easily, because we have seen that ni's are function of xi and eta, like this one. So, del n1 over del xi, del n1 over del eta, and so on can be found out explicitly from these equations. So, that really means that value of B can be found out actually. Yeah. So, and this B will be as a function of xi and eta, and that B, which is a function of xi and eta, we can put it here and we can integrate it in the new domain, that's xi eta domain, and you can find out the stiffness matrix. So the method is not different from what we have done in 2D heat transfer problem. It's exactly the same. It is not different from what you have done for the triangular isoparametric element. It's the same thing here. However, the domain here is not triangular, but rather a quadrilateral basically. Yeah. So once you find out the stiffness matrix using these equations, next thing will be to find out the force vectors, and for that you have F B vector due to the body force, and that you know this is equal to nt b d omega. Okay. So n we already have in terms of, this is in xy system. So n is already in terms of xi eta. So we have to convert, it's automatically already there. B is a body force. If this body force is a function of xy, then we have to convert this into xi eta by the relationship we have, x equal to summation of n I xi. So that we can use, and y equal to summation of n I times y I. So that we put inside this one, and it will automatically be converted to xi eta system. Yeah. So both two are now xi eta system. Only thing is we have to integrate in the xi eta system. So hence we equal to xi eta, and we have nt b, and then we have the j, determinant of j and d omega. Which one? This d omega is basically the new area, or we can also write it as like this one. So we have eta minus 1 to 1, minus 1 to 1, and nt b j, and you have d xi d eta. Okay. So you can write it like this one. Okay. So in fact we should have written ke also like that. So let's write it. So ke is equal to minus 1 to 1, minus 1 to 1, and bt db j and d xi and d eta. So we can also write k in this form. Yeah. Ft also, let's convert that also. Let us see. So ft we wrote it as comma, and then nt t d like this one. Okay. So now the you have to convert this into the new system. That is the only thing here. So all others remains the same. So here has to be integrated in xy coordinate systems. To convert from xy system to xi eta system, we have to use the original equation between x and y, between xy system and xi eta system. So here pardon me, so this has to be d eta here, and here this has to be x like this. Okay. Okay, please note the corrections here. So we can make use of this relationship, and also you have to notice that there are 4 sides, so there are 4 boundaries. So let us say this is gamma 1, this is gamma 2, gamma 3 and gamma 4. So accordingly the original equation will be in terms of all the 4 gammas. So we can write it as this is gamma 1. So NT TD plus gamma 2 NT TD gamma plus gamma 3 NT TD gamma plus gamma 4 NT TD gamma. Okay, so now let's write it d gamma 1, d gamma 2, d gamma 3 and d gamma 4. So indicating the variation along the 4 boundaries, 4 sides basically. Now these d gammas are in the original xy system. So we have to convert that into a xi eta system, and for doing that we can make use of this system, this conversion system or all these. So let us say for example gamma 1. So if you see here gamma 1 is basically is a line between x1 y1 and x2 y2, and this is what the this sides 1 2 corresponds to here, 1 to here, where eta is equal to -1 and xi changes from -1 to 1. So basically here d xi is equal to d eta equal to 0 in this case. Eta is not changing. So here if eta is not changing, then d eta here, d eta will be 0 and only d xi will be there. So on gamma 1 d eta equal to 0, put 0 here, then d xi is there. Okay, then this you can find out. Okay, and here accordingly dx and dy can be found out from here. Okay, but how are the dx and dy related? They d gamma actually, so d gamma 1 is nothing but equal to root under dx square plus dy square. Okay, so this relationship we can use it to find out d gamma, where dx equal to, where dx and dy can be found out from here for different gammas. For gamma 1 for example, d eta will be equal to 0 and d xi will be non-zero. So we get dx and dy both terms of d xi. Okay, so that means if you put value of dx and dy, we will get this d gamma 1 in terms of d xi 1. There will be some value here plus d xi, yeah, and that you can put here and then you can integrate. In that case this will be just right, there will be some value here, and either it will be d, in this case there will be d xi. There will be some value here that you have to work out based on the relationship here. Okay, the exact values can be easily found out for this, the value which has to be there within this bracket, and in order to find it out we have to use this relationship as I said earlier. So for first boundary, this one, yeah, what you see is d eta is equal to 0. So we put d eta equal to 0, what you get is d xi only. So what you get, dx equal to dA del x over del xi d xi, and dy equal to del y over del xi d xi. So same value, if we put it there, we will get del this root under del x over del xi square plus del y over del y over del xi, okay, square again. So this is what we will get, and of course we have to calculate these things when for that line only, for gamma 1 only, that is here eta equal to -1. Okay, so we have to put eta equal to -1 in this one, and then we leave d xi, because it will be integrated in terms of d xi then. Okay, and then we integrate. Similarly, you have to repeat it for gamma 2, gamma 3, gamma 4. Okay, more you can learn when you are actually solving the problem. Okay, so we will see that later. Okay, thank you.